Hello everyone and welcome to another video. So today I want to continue our discussion on calculus and integrals in particular by extending our discussion now to double integrals. So I like to start thinking about double integrals by taking a step back and thinking about just normal single integrals. So in this picture over here we can see your traditional function. You've got some function f, which is a function of x. So you've got a sort of one-dimensional domain. And now what we want to do with most traditional normal integrals is try to integrate between some lower limit and some upper limit. And all we're doing by integrating this function over that domain is we're effectively trying to calculate the area underneath this curve between the minimum and maximum, or in this domain, right? And we saw that one easy way to think about doing this is just say, okay, I'm going to pick some location here. Let's call this x of k. All right. And then we are going to look at some region around that. Maybe we're going to call this width like a delta x. Right? And then that gives us a width or a base of a rectangle that you can kind of draw like this, right? Okay. And we take the functional value f at that point xk, right? And you can see now you have a base of a rectangle and a height of a rectangle. So I can get the area of this small little sliver here by basically just taking the functional value, multiplying it by this delta x, right? And then to get the area of the entire area under the curve, I just need to sum this up over the entire region from x min to x max. So basically this is the Riemann sum sort of approximation of an integral. And as we make these delta x's smaller and smaller and smaller, we basically can get and define that is what a normal single integral is, right? It's basically looking at the area under the curve, and you can think about it by just finite differencing or discretizing the domain of integration and then just adding them all up, right? Adding up all these tiny small areas, right? So again, that is a single integral. So now let's think about what might a double integral look like. So in this single integral case, there was one sort of independent parameter x, right? But what if your function is a function of, say, two variables of x and a y? So that's this picture over here. So now we have a domain in x and a domain in y. So really now our domain of integration, instead of being a line like it was in the one-dimensional case, it's now it's like some region. Let's call this thing some region, the same domain of integration, right? Except now you can see that x runs from some minimum to some maximum, and y also runs from some minimum to some maximum now. And now over this domain, just like we saw earlier, there is a function overlying that domain, right? So now in this case, since there's two independent variables, instead of having a line like we did in the single case, we now have a surface that is going on top of this domain, right? So again, I've tried to draw this as just some section of a function, but again, you think about this, it's now a surface going over this domain. So now you can think about the exact same idea of, okay, if I want to do some sort of double integration, I basically want to take a look at this domain of integration, and I'm going to now come here and try to make a small little area. Let's call this area delta A or something like that, right? And I can look at a point here at x and y m or something like that, right? That's the location of x and y. And then you can think about this as going up to the surface just like we did earlier, right? So now instead of being like a rectangle, it's almost like this tower or this little cube, right? Which has a base of delta A as the area and a height, right, of f of x n y m, right? It's the function evaluated at this location, right? So this term right here gives us basically the volume now of this little square. And if we now sum over all of the little squares in this domain of integration, we basically get the idea of a double integral. So now we can write a very similar idea now where x goes from some minimum value, as you see here, to some maximum value, and y also goes from some minimum value to some maximum value, right? And now if I try to integrate the function over this infinitesimal area dA, right? What we're really doing is we are calculating now the volume underneath this surface, right? That's the idea. So with a double integral, we're getting the volume under the surface. With a single integral, we're getting the area under the curve, right? So again, it's just an extension of this idea to one additional dimension. what's interesting to think about here is let's look at this little dA, right? This little small area delta A. If you think about this and you look at it, you can see from this picture that dA is really, there's a dx, right, in this direction, and a dy in this direction. I apologize, this is getting a little bit small, right? But I think everyone sees what we're saying, is that this area, I can also write this as dx dy, right? Because it's a delta x and a delta y, right? That's what the area looks like in this picture. And furthermore, the order actually doesn't matter. So you could also write this, maybe, shoot, I kind of ran out of space. Let me come over here and see if we can, I'll do it like this, right? The other way you could have written this is you can also write this by going in the opposite direction first. You can go dy dx, right? That's the same thing as this same dA. The only thing we have to be careful about is these limits of integration. So the inner limit of integration in this case is dy. So we have to go from y min to y max first, and then from x min to x max, right? And again, I think the easy way to think about this is I always like to put parentheses in here. So this one is first, right? That's the inner one. And then similarly, here's the inner integral over x first, right? And we're going to look at this in an example in just a second. But we see that, again, this is the idea with the double integral, is that we're now calculating the volume under the surface. And all we're doing is basically looking at infinitesimal areas dA over the domain of integration. Now, in this picture, we've drawn it as a perfect rectangle, so why don't we start with that example? Let's look at an example of how do we perform a double integral where you have a perfectly rectangular domain of integration. All right, so let's look at an example. So we want to evaluate this double integral where the function is this, x plus 2y, and here's the region of integration, or the domain of integration here, defined by this. X has to run between -1 and 1, and y goes between 0 and 2. So the first thing I always like to do with double integrals, and we're going to see that this is actually going to be very important later, is I like to draw the region of integration. So let's just quickly do that, and you can see that it's actually really easy to do for this case. So in this situation, x goes between -1 and +1, and y goes between 0 and 2. So the region of integration looks like this perfect rectangle like this. So we're going to integrate over this domain of integration, right? And if you look at this long enough, this function f, it's actually just a plane. In fact, to better visualize this, instead of me trying to draw this, I'll just show you a little movie over here where I plotted this up in MATLAB and we spin it around a couple of times, and you can see the perfectly rectangular domain of integration, and you can see this plane on top of it. And what's interesting is you can kind of see that in some areas there's actually kind of negative volume, right? Because in some situations this function f actually kind of goes below the xy plane. But in any event, we can still do the same like we did with a single integral, where you might have positive integrals and negative portions of the integral, and they'll just kind of cancel each other out if appropriate, right? So that's the same situation in this case. So again, that's what it looks like. So let's go ahead and see how can we actually compute this now. So to do that, okay, let's look at this integral, okay? So again, what we said is this thing can just be written as, okay, here's the function, it's x plus 2y. And now this dx dy, let's keep it in this order. Let's integrate over x first and then over y. So since the inner integration is going to be performed with respect to x first, we use the x limits on this inner integral. So this goes from -1 to 1, and then the outer limits of integration are the y. So this is 0 to 2. Okay? And again, what might help us in this case is let's go ahead and maybe draw a little parentheses around this, and let's do this inner integration first. So all we do is everything just in the green, and we see that this is just a normal single integral. So maybe let's call this out here. This is a normal integral, right, with respect to x. So in other words, what we're going to do is we're going to consider that y is constant, right? Just treat it like some number, right? So, okay, let's go ahead. Let's write the outer integral, because we're not touching that, right? So we have the 0 to 2y dy. And now the thing inside, we can easily integrate this because, well, we're going to consider this y as constant. So this guy right here, this becomes what? This is x squared over 2, right? And then plus 2xy, right? Because again, we're just going to consider this y to be a constant. So this is just some number. So you integrate it with respect to x, you get this, right? So this is the indefinite integral of the inside. But again, we got to remember that we are actually going to have to evaluate this between x is equal to 1 and x is equal to -1, right? Because this is a definite integral, right? So again, let's just keep going. Okay, so now let's do the upper limit. That's over here. It's when x equals 1. So we have the what? This is 1 squared over 2 plus 2 times 1 times y, right? That's the upper limit. And then we subtract off the lower limit, which is -1 squared all over 2 plus 2 times -1 times y, right? Okay, and then we integrate with dy, okay? All right, so you do all of this simplification and all this math. I think what you end up with here on the inside, if you do all this right, is it just comes out to 4y. There we go. Okay, so all this gobbledygook just turns into 4y. Okay, so then doing this integral, we see again, this is now just a normal integral. And one thing to note is at this step, we have integrated out x. So you should be left with something that has nothing to do with x, right? Because we integrated over x, so there should be no x terms left. So again, this just turns into a single normal integral with respect to y now, right? So we can do this like anything else. So what do we end up with? This is what is it? It's 2y squared, right? And again, evaluated between y is equal to 2 and y is equal to 0, okay? Okay, so just working that thing out, I think you end up with, gosh, we can do this here, right? This is 2 times 2 squared minus 2 times 0 squared, right? So I think we just end up with 8 at the end of the day, right? So there you go. This is kind of not too shabby, right? And just to prove this to you, why don't we go ahead and make sure I did this correctly. I'll show you a screenshot of me doing this in Mathematica, and you can see the code in Mathematica is actually very similar to what we were just talking about in the sense that you just have to perform a single integration with respect to x first and treating y constant, and then you just do another integral with respect to y, and you'll end up with your number, right? One thing to maybe note here is that if you think about this long enough, what's interesting is that in this case, with our double integral, right, we looked at a sort of definite double integral in the sense that there were definite limits of both x and y, right, in this case. This is what you're going to typically see with double integrals. Remember, with a single integral, you can definitely have the idea of an indefinite integral, right? Because there's a concept of an antiderivative of a function with respect to a single independent variable, but you don't really have the same idea of an antiderivative for a function with two independent variables, so an indefinite double integral doesn't really make sense. But and again, that is why you're going to see most of these double integrals are pretty much all definite double integrals, okay? So, yeah, this is kind of interesting. It's pretty easy, you can see, in situations where the area of, or the region of integration is a simple rectangle, this is not a problem. But now that we have some practice of this, give me a second to erase the board and let's talk about a few properties of double integrals. All right, so now that we have a rough idea of how these double integrals operate and what they physically mean, let's talk about some properties of double integrals. So again, all of these properties apply to a double integral over some region or domain of integration R. Now, what's interesting about this is this region doesn't have to be perfectly rectangular like we saw earlier. In fact, while we're going through these properties, why don't you keep in the back of your mind and start thinking about what if this region was something else? Some potentially interesting odd shape maybe in the XY plane. So even in that situation, all of these properties hold because, like we said, we know what we're really doing with these double integrals. We're really just trying to calculate the volume of a surface over this region R. So again, this region R doesn't have to be a rectangle. It could be some other shape. And even if that's the case, we can see that, you know, this is your standard property, just like we saw in normal integration, that if you have some function and you're multiplying it by a constant, this constant, as long as it's not a function of x or y, it can come outside of the integral, right? And that's just like we saw with single integrals, so nothing major there. Let's look at this other property. Let's say you have two functions, a composite function, which is the addition of f and g, and you're again integrating this over that region R. Well, just like a normal single integral, you can break this up into two separate integrals where you first integrate f over the region R, then you integrate g over the region R, and you add the two together. That's the exact same thing as adding the two functions together and then performing the integral, right? Now, this other one is also very kind of interesting. Let's say that you are again trying to integrate this function over the region R. Well, what if this region R, what if we want to break this up into maybe two subregions, like an R1 and an R2? So again, we're just adding up small little volume chunks over this region and this region. So really, you can break up this single integral into two separate integrations where first you integrate over the region R1 and then you integrate over the region R2 and then add them together. So again, nothing earth-shattering here. A lot of this is going to start making a lot of physical sense, especially because we see that it's just talking about calculating volume underneath this surface, right? So this, you can apply some of these properties and some of these ideas to come up with things like the mean value theorem, right? So the mean value theorem for double integrals, it basically says that as long as this region R is simply connected, right, that it's, you know, effectively you don't have any holes or any or disjointed parts in it, right, then there's at least one point, let's call this point x naught, y naught, somewhere in this region such that this double integral is basically just equal to the area of this region times, basically this, you can think about this is like the average value, so to speak, of the function, right? So this is basically saying that you can take this complicated volume here and basically turn it into an area times some height, right? That height being the average value. So you can kind of think of it as a volume could be this thing with an interesting cap on the top, or you can make it a flat value at that mean average value, right? So again, these are some interesting properties of double integrals, and I think a lot of this extends directly from our ideas of single integrals. But what I want to talk about now is, okay, what do we do if we have a region R which is not a simple rectangle? How do we handle that? All right, so now let's talk about what happens if the region is not rectangular. So again, just refresh your memory, with a rectangular region of integration or domain of integration, this was pretty darn simple, right, to evaluate this integral. In this case, let's do it over y first and then x, right? So y we see runs from y min to y max, and then x runs from x min to x max, right? Now, the issue is, like, let's consider this other region down here, which is definitely not rectangular, right? So the question in this case becomes, what does this double integral over the region look like, right? And again, let's think about maybe what if we want to go over y and then x, right? So what are these limits of integration? Because we don't want to describe this rectangle, we want to describe this interesting shape down here, right? So what we can do is, in this case, let's go ahead and say that, all right, if I look at this, there's still sort of an x min and an x max, so to speak. Let's maybe call this like a and b, okay? So we see that x still runs between a and b, but now y actually runs between different values. And I always like to draw myself a little arrow to help me remember which way I'm going. Okay, so let's say we want to integrate between y, which is actually now down here, and we see that the y value is actually a function of x, right? So this lower portion, maybe we can kind of color this in a sort of a different color. Let's do this sort of in orange. I'll try to trace over in orange. This lower curve of the surface here in orange, right? This is some function, let's call it g of x, right? Because it's a function of x, right? It looks, in this case, looks like some kind of quadratic or something like that, or cubic. I don't know. It's just some function of x, right? And then the upper surface of this object as well happens to be able to be drawn in a, let's do this in purple, right? Maybe I'll draw it like this, right? Okay. So this purple is some other function. It's like an h of x, right? Again, it's some function of x, but it's different than g because you can obviously see that the shape of it is different, right? Okay, so now what's interesting in this case is this is sometimes what referred to as a type 1 region. And it's a situation where we can describe this region R, right? This is what I'm interested in, but we can describe this region R as basically what? It's all of the x and y locations such that x is actually, we see x runs between a and b, right? And then all of the y values actually run between functions, right? So the y value is between g of x and h of x, right? So this is sometimes kind of, like we said, referred to as a type 1 region because you can describe it this way, okay? So in this situation, it's actually beneficial to write it, this region R in this fashion. So we see that this double integral, this region now, we see that y runs between actually a function now, which is g of x on the lower limit and h of x on the upper limit. And then x runs between a and b, right? Okay, so in this case, this is a very good way to evaluate type 1 regions. Okay, so in this case, we can use this formula to evaluate a double integral over a type 1 region, right? Now, I'm sure you're thinking, okay, type 1, that must mean there's like a type 2 region, and you'd be absolutely correct, right? We can redraw this picture. In fact, I'm trying to figure out where's a good place to do this to have a little bit of parity. I guess we can do it right here. Let's do it over here, okay? So again, let's do the exact same discussion, okay? Well, let's draw that picture again, and I'll try to replicate it as best as I can. I'm not the best artist, but I think hopefully you'll get the rough idea. I tried to make that look the same as that over there. So it's the same region R, okay? And now what we can do is let's go the other direction. So again, I'm going to draw my arrow here in red to say that we actually want to integrate over x first and then y. So in other words, what I want to do is I want to go ahead and evaluate the double integral of this function, f of x, y, but I want to go over x first and then y, okay? So again, we make the exact same kind of analysis except sort of in the other direction, right? So we see that, okay, there's like we see that y runs between kind of a y min and a y max. And in this case, just so we don't get them confused, I'm going to call this lowercase c and lowercase d, right? Just so we don't get it confused with a and b, okay? And now what we can see is, again, now the x values, right? The x values go between two curves, right? So the first curve, again, just like we did earlier, let's do this in orange, right? So here's the bottom, so to speak, or the lower limit of x, right? So this is now some function of y. Let's call it p of y, right? Again, it is a function. The x values can be looked up or specified if you know the given y values, right? So this describes this curve here, this p of y function. And then the upper limit, right, is this half of it, which again, let's do it in purple. And this is now referred to as, let's call it, how about q of y, right? So again, we see that this is what's referred to as a type 2 region. So if you can go ahead and define your region R, it's all of the x and y values such that now the y values are actually between these values c and d, right? And the x values are now between functions, right? So the x value runs between p of y and q of y, right? This is a type 1 region, and in that case, this double integral is, again, the same idea. We just need to evaluate the x values go between what? Well, the x values go between these two functions, right? A p of y and a q of y. And then the y values go between simply c and d, right? So this is a nice, easy way to go ahead and evaluate type 2 regions, right? So here we go. This is a way that we can go ahead and evaluate a double integral over either a type 2 or a type 2, either a type 1 or a type 2 region. You just need to identify which one is easier to describe your region of integration. So I think this will make sense if we look at a concrete example. All right, so let's look at an example over here. So I'd like to look at the double integral of, actually, let's use that exact same function we looked at earlier in the discussion. Basically, that was this plane here. But now instead of evaluating it, the double integral over a rectangular region, let's do it over this funny shaped region you see here, okay? So just staring at this, in fact, I left the discussion on the board where we were talking about type 1 regions, because if you look at this, you can easily see that it's much much easier to describe this as a single type 1 region than trying to break this up and do it as type 2 regions, right? So this is very easy to first integrate over y and then go over x, because we can see that there are distinct instant parallels to what we saw earlier, right? So in this case, here is our a value of -1, here's our b value of +1, and we see that the limits of integration for y are between these two functions. So again, let's look at the lower limit function, which I think we colored in orange earlier. That's this curve down here. So this is basically our g of x, right? So here's g of x. So this is the function, right? Here it's the function of x. It's 2 times x squared. That describes this orange line down here, and that's the lower limit of integration for y. And then the upper limit of integration, we can easily see, is just this one here in purple, just like we illustrated earlier. That's this function, which is just some other function of x, but we call this thing h of x, right? Okay, so with this, it's pretty much just inserted into our expression here to calculate the integral of this thing, right? So let's go ahead and do that right now. So let's go ahead and write this thing as x plus 2y, right? Oops, excuse me. And then we're going to run from, oh gee, I got to get an eraser. I'm kind of messing this thing up. 2y. We're going to run from dy and then dx. So the first thing we're going to do is y goes between these two functions, right? So we have 2x squared on the bottom, and then it runs all the way to 1 plus x squared on the top. That's the x limit, or excuse me, the y limits, and then the x limits of integration are between -1 and 1, okay? So again, I like to put these things in parentheses so we can focus on one of them at a time. So let me go maybe put some brackets here. Let's just look at the y integration, right? And again, this now becomes a single integration. And what we do here in this case is we are going to go ahead and consider x to be constant. Right? It is not a function of y, and we are only integrating with respect to y here. So that's not too shabby. Integrating that thing becomes, what do we end up with? We got what? X, y, the integrand, plus y squared, right? That's the inside. And then this whole thing, right, is evaluated from y equals the lower limit of 2x squared to the upper limit of y is equal to 1 plus x squared, right? So it goes from this lower limit to this upper limit, right? Oh, excuse me, this is just what's in the parentheses, right? So now we still got to take that and we got to integrate with respect to dx after we're done between -1 and 1, right? Okay, so let's just do one more step of this just so we're explicitly clear. And in fact, maybe what I'll do is let me erase some of this so we can kind of keep going down in one area. We'll see if we can fit all this in. So I'm going to take this and evaluate it at this upper limit. So everywhere you see a y, I need to shove in 1 plus x squared, right? So we have, this is x times 1 plus x squared, right? Plus 1 plus x squared squared, right? That's this upper, this value evaluated at the upper limit of integration. So maybe let me put this in brackets. Right, this, and now I need to subtract off this thing's evaluated at the lower limits of integration, right? So again, I take this thing and I have x times, now it is 2x squared, right? Plus 2x squared squared, right? There we go, that's that thing. And again, we got to evaluate this entire thing dx from -1 to 1. Right? Okay, great. All right, this is a little bit ugly, but again, let me stop and pause at this step and notice, right? The fact is, because we integrated with respect to y, right? We basically get rid of everywhere you see a y, you are plugging in some function of x. So here, the integrand that we're dealing with now is only a function of x, right? That's what makes this beautiful, and that's what makes this easy, is that you are guaranteed to be not left with any y terms after this step. So at this point, it's just basically algebraic simplification. So let me save you that boringness, and let me tell you that this whole integrand here, it cobbles down to, what is it? I think you get 1 plus x plus 2x squared minus x cubed minus 3x to the 4th. There we go, dx. Okay, so again, this is boring because this is now a simple integration, a single integration of, it's not even anything complicated, right? It's a polynomial. So this is now turn the crank to get yourself this definite integral. I don't want to bother with this. I'm going to go to Mathematica. In fact, here, I'll just show you my code here. You can perform this integration in your sleep, right? Or ask some high schooler to do this for you. And I think at the end of the day, you come out with this thing comes to be 32 over 15. Right? So there you go. That's your answer, okay? And again, it just shows how to go ahead and compute this using our successive two integration schemes. In this case, using a type 1 region, but you can easily see that depending on how your region is set up, perhaps a type 2 calculation is easier. So we'll get some exercise on that in the homework, okay? All right, give me a second to erase the board and let's talk about one last thing. All right, so now let's take a moment to talk about performing double integrals in polar coordinates. So just to refresh your memory, we had a dedicated other video talking about polar, cylindrical, spherical coordinates, all that kind of stuff. So feel free to check this out if you need a quick refresher on polar coordinates. But getting back to this discussion at hand, just to refresh your memory, right, what we were really talking about is performing a double integral over some region R. And what we were doing earlier is we kind of discretized this using Cartesian coordinates in the sense that we broke up this region R into all these tiny little infinitesimal areas dA, and we looked at them having a width, so to speak, of dx and a height of dy. Therefore, you multiply dx with dy, you get dA, right? So this is what we did earlier, is we basically gridded this up in a giant rectangular fashion, right, using Cartesian coordinates. Well, there's nothing to say that we have to discretize using rectangular Cartesian coordinates. In other words, let me draw this picture again, right? So it's the same region. Let's just try to chop this up into different infinitesimal areas using polar coordinates. What I mean by that is, instead, let's consider radial distances from the origin, maybe something like this. I'll draw it like this, okay? And maybe I'll draw two of them like this, okay? So what we've got now is a little region in space which looks something like this, right? So this is now dA, right? Where now this dA unit is located at a radius, let's call it R from the origin, okay? Okay? And the base, so to speak, this distance, let's call that a change dr, right? That obviously makes sense, right? You got a radial distance, you just increase that radial distance by dr, and you get this base of this little infinitesimal kind of rectangular-ish area. Now, where it gets interesting is the height, this sort of arc. You can see that this arc right here is basically part of a circular arc, where the arc amount here, let's call this d theta, right? Because again, theta is measuring the angle from the x-axis to this location, right? That's how polar coordinates worked, right? So what I'm getting at here is this distance, so to speak here, the height of this rectangle, if you think about this long enough, it's the radius times the angular displacement d theta. In other words, this term right here is actually r times d theta, right? So what we get here is that this dA, it's basically the base dr times the height, which is r times d theta, or r dr d theta, right? So the thing I just want to stress, and I'm going to actually underline this in pink, is that there is this extra r term that gets introduced when we convert the problem to polar coordinates, right? So in other words, if we want to look at, again, the general idea is I want to calculate a double integral of some function over some region R. If I want to now do this in polar coordinates here, what we really are talking about is we are now going to have to convert the function f to be in polar coordinates. Basically, it's a function of r and theta. But now this dA, we see, turns into actually r times dr d theta, right? So again, keep this in mind that when you do this conversion, there is going to be this extra r term that shows up. And I guarantee you this is the number one mistake that people make, is they neglect this extra r term that gets introduced in the conversion, right? Okay, so that's a general idea. So tell you what, let's look at a concrete example. So let's look at this. Let's say, again, I want to just do this. I'm trying to calculate the volume of this function, basically the volume of f under, I keep saying this wrong. I want to look at integrating f to get the volume that is between the region R and the function f, right? That's just a general idea of a double integral, all right? So here is my function, right? It's just this thing. And if you stare at this long enough, in fact, we'll go over to Mathematica and look at this, but you'll see that this is basically the top half of a sphere of radius 2, okay? So again, we could stop right here and you could just go ahead, draw the region like we saw earlier, like this is the region I'm interested in. Let's just look at it in the, sort of the first quadrant, right? So I want to integrate, think about it, there's a sphere on top of this thing. I just want this first quadrant. So we could treat this like a type 1 or a type 2 region. We could do integration in Cartesian coordinates like we did earlier. But looking at this region, we see that this region is very easily described in polar coordinates. In other words, it's all the x and y locations such that, it's all the r and theta values, right, where r runs between 0 and 2, right? And then theta, whoops, keep doing this wrong. Theta runs between 0 and pi over 2, right? So it's very easy to describe the region in polar coordinates. Therefore, we probably want to think about evaluating this using our polar coordinate system. So to do that, what we should do is, okay, first things first, we are going to convert f of xy to f of r and theta, right? So we basically want to convert this to polar coordinates. So recall from our discussion, that just means everywhere you see an x, you insert r cosine theta, and everywhere you see a y, you insert r sine theta, right? That was the conversion from Cartesian to polar. So you put that into here, and in fact, you know what might be good? Let's actually jump over to the computer and do the rest of this in Mathematica, just so we can kind of visualize some of these objects and do some of this integration. So let's hop over to the computer and we'll continue with the example. All right, so here we are in Mathematica. So the first thing I'm going to do is just go ahead and define our normal function in Cartesian coordinates, and then let's perform the conversion to polar coordinates like we said by basically inserting everywhere you see an x with an r cosine theta, and then replacing everywhere you see y with an r sine theta. So going ahead and inputting that, we see that here are our two representations of the function. And what we can maybe do is let's plot both of these. Oops, so let me take this part off. Sorry, I just want the plotting part. So great. Let's just use plot 3D to plot the normal Cartesian representation between these x and y values. And then we'll use revolution plot 3D to plot the polar version of this between this radius and this theta values. So again, entering these in, we'll see that yes, these are both basically the same equivalent representations, and you see that they're just the top half of a sphere of radius 2, right? So that's what the function looks like. So now what we can do is we can go ahead and write the double integral. So what we're going to do is, let me go ahead, I've actually prepared some of this off screen so you don't have to see me typing this in, but we can now go ahead and evaluate the double integral using the polar formulation. So in other words, we want this integral, this double integral of the function over the area. But when we convert the dA area, again, notice here that this becomes r times dr d theta, and then we can insert in our function that we had above. So again, just showing that, let me go ahead and I'll copy paste in what we've got as the next line, all right? So let me line this up so we can see this a little bit more easily. And actually tell you what, let me delete these pictures so we can see everything in one spot, all right? So here is our polar representation, right? It's square root of 4 minus r squared. So that just goes in right here because that is f of r theta. But again, remember right here, here is this r, this little insidious r that you have to put in, which is sometimes very easy to neglect, all right? So at this point, I think what we can do is let's go back and do this like we did earlier, and I'll put some parentheses around this to denote that we want to do this integration first. And this is actually quite simple. So this is just, let's go ahead and do this. Integrate, again, it's f polar of r and theta, right? So this is the square root of 4 minus r squared, but then I have to add the r times r, right? Great, and I'm going to integrate this from r going from 0 to 2, right? That was our limits of integration. as you see here. So this is basically, I don't know, term 1 is this. So you integrate this and we just end up with, it looks like in this case, just a constant of 8/3, okay? So then this becomes, let's go ahead and write this down here, this entire inner integral becomes just 8/3. And now you see this is actually really simple. So the final answer is we just need to integrate this first term going from theta from, what did we say? In our case, it was, I think, 0 to pi over 2, right? Yep, that's our limits of integration for the region. So you integrate that and you get this. This is our final answer, 4 pi over 3. And again, we can double check this because we know that what we were trying to do is basically look at a, oh gosh, I deleted the picture. But you know that we were trying to integrate. Let me just copy paste this from over here, just so we can look at the picture. It looked like this, right? It was the function f was basically the top half of a sphere of radius 2, but the region of integration was only a quarter of this, right? So really what we're talking about getting is we're getting the volume of 1/8 of an entire cylinder or sphere, right? So the volume of a sphere, right, isn't that pi or 4/3 pi r cubed, right? That was the volume of a sphere. And again, we want to say the radius here is 2. So this is the volume of an entire sphere, but we actually want just 1/8 of this, right? So again, if you do that, we end up with 4 pi over 3, which is exactly what we got earlier. So this checks out, and this seems to work quite nicely. All right, so to close, now that we have a pretty good feel of how these double integrals operate and what they do, let's talk about a few applications. So obviously we saw that the primary application of these double integrals is to calculate the volume that is underneath a function f over some region r, right? So this is pretty much what we've been doing the entire discussion. Now, if you extend that idea and think about this, if you just use f of just 1, right, a single constant 1, you can basically use this to calculate the area of r, right? So it's, again, you just perform this double integral over a function f of 1. That gives you the area of the region r, right? Extending this idea even further, you can do more interesting things as well. So, for example, what if f is something like the density distribution over this region r? So it's in units of kilograms per meter squared. So it's like a density per unit area, right? So if you have a function that describes how dense an object is at any given xy location in the plane, you can then talk about things like you can get the total mass of this area over the region r, right, by just performing that double integral. That's what it's going to physically give you, right? And then you could play some games with this. Like if you look at calculating the double integral of x times f, right, times this density distribution function, and then just normalize it by the total mass m that we just calculated here, you can basically calculate the center of gravity in the x location of any sort of complicated region r with possibly varying density distribution and here f, right? So this is pretty easy. You can do the same thing for y, and then you can even do things like get moments of inertia about a complicated physically odd-shaped object with odd density distributions. You can do it like this, or calculate the moment of inertia about the other axis just as easily. Just kind of keep in mind that you kind of need to switch the x and the y. So the moment of inertia about the x-axis, you actually use a y squared here. The moment of inertia about the y-axis, you use an x squared here. So again, it's pretty fascinating, and there's a lot of different applications of double integrals. And in fact, I hope you'll join us at our next discussion where we're actually going to look at how do double integrals potentially interact and relate to single line integrals. So we're going to be looking at Green's theorem next and continuing our discussion and investigation into vector integral calculus. So with that being said, I think this is probably a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. If you scroll a little ways down and click on that button, it actually really does help me continue making these videos. And remember, the new videos come out every single Monday, so I hope we'll be able to catch you at one of these future discussions and we can all learn something new together. So until then, I think I'll sign off. Talk to you later. Bye.